Hello. Welcome back, everybody, to the next stream. Good to see you. And we are going to crack on with finishing off the exam paper that we didn't quite finish last night. So I'll just put the camera on straight away onto my screen. Hello. Just check the sound. Yeah, good. That's good. I can always hear myself. So last night we were doing the exam paper here, if I can find it. That's the next one we're doing. We were doing the database question, and we looked at this question here about primary keys, and we ran out of time to do the SQL one. I didn't want to do this one last night because in case it sort of took a bit longer. So complete the structured query language statement to return the number of cans the shop has in stock. So we're going to write the SQL. They've given us the template for the SQL, which is always nice. And they've also given us a sort of basic outline of what we need to fill in here. So we can see we've got brackets here. So we're going to have some kind of function. So for your syllabus, there's only two types of function. There is count or sum. So a bit of a clue there. See if you can do this without me explaining it. I'll give you a few minutes, and then after that, I'll explain it if you're not sure what you're doing. If anyone wants to put their answer in the chat, feel free. And someone said about the 50-mark question. I'll talk about that in a minute, actually. Yeah, so we're doing part B, the SQL statement. Okay, so no one's putting anything in the chat, but I'll explain it anyway. So when we're doing our SQL statement, we're basically we're telling the database we want to search our database for certain criteria. And in this case, it says that we want to have the number of cans the shop has in stock. So basically, we're going to count this field here, the number in stock. Obviously, in this case for cola, it's 30, but we're going to add up it for everything. So that means we need sum. So adding up means sum. And then in our where clause, I will write it out in a moment, but in our where clause, it says it's the number of cans the shop has in stock. So basically, we would use the container field where the container equals a can. So if I write that out, it will be select some number in stock from the name of the table, which is, I moved it, soft drinks, capital S, capital D, from soft drinks, where container equals can. Now, when you're searching for a string, it's capital C, isn't it? You can just put can. It's better to put quotes around it. So if it is a string like that, put quotes around it. So you can see there, they've put the basics of it in there for us, and we've got the brackets, so that means it's a function, but it is select some number in stock from soft drinks where container equals can. They will have some kind of SQL question, so do make sure you learn that. It's a good way. Databases, logic gates, a good way to pick up lots of marks without doing any programming. Now, as I said last night, I'm not going to do the 15-mark question for this because this is one that I did last week with my live students, and it is also in the recorded course. So if you are a recorded student, then just go to, I think it's lesson 51, and I talk through this one in that lesson. So I don't want to repeat it all. We need to use the time to do other questions. But I will do the next one, which is the 15-mark question for the next paper. We're going to do a March paper again. So we're kind of rotating around some of them, and we're going to do, that's the answer, by the way, as you can see. Yeah, so we're going to do a March paper from 2024. So if you want to try and get hold of this one from the papers that you have access to from me or somewhere else on the internet, it's a February to March paper from 2024. And we're doing, obviously, the theory paper first. So the first question is, computers represent, oh, actually, we've got two tick boxes, so I'll give them both to you at the same time. Tick one box to show the reason why computers use binary to represent data. Is it computers only allow ones and zeros to be entered? Computers are made of switches and gates that can only be on or off. Binary does not need to be converted into other forms of data to be displayed, or both computers and humans can quickly process binary data. And then we've got American Standard Code for Information Interchange ASCII denary number for the character N is 78. What is Q? Okay, so the first one is B. Computers are made of switches and gates that can only be on or off. So computers only allow zeros and ones to be entered is false. Binary does not need to be converted into other forms of data to be displayed. That is also false. and both computers and humans can quickly process binary data. Well, I don't know about you, but I definitely can't process binary data very quickly. So it is actually B, computers are made of switches and gates that can only be on or off. And it's logic gates, basically. Now, the next question is unusual. So we've got the ASCII code for 78. So if you did my live lessons with me, you might remember the lesson that we did about ASCII, and I showed you the ASCII table, and then I'm like, don't worry, you don't need to learn it, but they do want you to understand how the ASCII table works. And this is what they're asking, is how it works. So if we think about the ASCII table, what they've said is N is 78, okay? So if N is 78, remember it just goes up. So we've got the alphabet N, M, I can't do my alphabet now. Q, L, M, N, O, P, Q. There we go. There's some alphabet. So we know that N is 78. So N is 78, and the numbers just go up. So O is 79, P is 80, which means that Q, which is what they're after, is 81. So M would be 77, L would be 76. So that's all they want you to know about ASCII. You don't need to remember these off by heart, just know that they go up and down. So Q is 81. And that was what they're after. And there we go. Yeah, it's 81. That's the A. I forgot to mention earlier, actually, with the 15-mark question, someone said they're going to do it in pseudocodes. There's absolutely no problem to do that. And actually, you might be the one who asked me, will I do the answers in pseudocode? I will try. But the thing is usually well, not usually, but always, the mark scheme has it in pseudocode anyway. So you're always going to have that advantage. Okay, so then it says here, give the binary number for the ASCII denary number for N. So basically, what is 78 in binary? So what is 78 in binary? And if they don't say, always do 8 bits. In ASCII, how do they do the smaller numbers? I'm not sure what you mean. Could you explain a bit more? Oh, okay. So if N is 78, what is 1? I don't think there is a 1, actually. Oh, I don't know. I think it starts at like 50 or something like that, I seem to remember. If you, I can't do it at the moment, but if you Google ASCII table, it'll show you what all the numbers are. Okay, so let's go through this. I'm going to go through it anyway, just in case there's some people watching who can't remember how to do this, how to do binary. Hopefully that's not you, but yeah, we'll do it anyway. So here we've got our columns. And we've got the number 78. Keep forgetting what it is, 78. So all we do is we say, okay, we start on the most significant bit. 128 is too big for 78 to go in, so it's a 0. But 64 isn't, so we can do that. 78 minus 64 is 4 from 8 is 4, 6 from 7 is 1, so we've got 14 left over. So that means that 32 will be 0 because 14 is too small. 16 is too small as well, so that's a 0. Nearly wrote a 1 there. It's a 0. But 8 is not, so we can have a 1 there. 8. So 14 minus 8 is 6. So we've got 6 left over, and 6 minus 4 is 2. So we can have a 1 there and then a 0 there. So it's 0, 1, 0, 0, 1, 1, 1, 0. Let's look at the next question. So basic binary, always in there somewhere. Explain how the word red is represented using a character set. 2 marks. Explain how the word red is represented using a character set. And by character set, they're talking about ASCII or Unicode. So really what they're getting at this is, you know, if we've got our ASCII code, so if we go back here, we've got our ASCII values for each letter. All we do is we store the ASCII value for each letter. So in this case, if we've got R somewhere, P, Q, oh, R down there actually. I know my alphabet, I do, honestly. P, Q, R, S, and we've got E somewhere further up. So we've got 82, 83. So it would store 82, or the binary equivalent, then whatever E is, and then, so say it's, I don't know, just anyway, and then whatever D is in the ASCII code. So it's storing the unique binary or denary number for each character in the order that they appear. So if we had, I don't know, pop, for example, POP, it would store 80, 79, and then 80. So that's what they're getting at. So if we have a look at the answers, I'll just show you what they've got in here. So we've got, it's a unique binary or denary number given, stored for each character. The code for R is stored, then the code for E, and then D in sequence. I think the in sequence bit's important. Okay, next question then. Sound can be represented as binary. Explain why recording sound with a higher sampling resolution creates a more accurate recording. 2 marks. And then our final question, give one other way that the accuracy of a sound recording can be improved. So they are either, what they tend to do in the exam actually, is when they get to this bit, they've asked you some binary, possibly some hex, and they might ask later on, they'll ask about either images or sound and resolution and how many bits are stored for each. So to answer this question, really what we're doing is we're thinking about what happens when we are turning that sound into a binary store. So if we think about that sound wave, the amplitude of the sound is recorded, and we have samples that are done. There's a certain number of samples done per second, and each line represents a sample taken, and the cross represents where that sound amplitude is. Now, the distance between the samples depends on the sample rate, which we'd look at in a minute, but the sample rate is just basically how many per second. So there's a few sort of terminology that they want you to know. The sample rate is how many samples per second. And usually it's sort of CD quality, we call it, is usually around sort of standard, around 44, well, I'll just say 44,000. There's a few around that, but 44,000, give or take, is roughly what is sort of a really good quality. Low quality would be 8,000, and high quality can go up to like 345,000 for really high quality. Now, what happens is when we take that sample, though, as the sound is measured, it's converted into binary. So whatever the measurement is of that, so I don't know, it might be whatever the sound measurement is for that sound, it's stored as binary. So this one is stored as binary, and whatever the amplitude is. So what they're really talking about here is the resolution is not the rate, so how many times you're doing it, it's how many bits you're storing for every sample that you take. So the resolution is how many bits per sample taken. And I think normally it's around about 16, but you know, if you think about it, it's the same with anything in computing. The more bits you have, the more storage you're going to have, the better quality it's going to be. Doesn't necessarily mean it's fast, but you know, it's the same with like CPUs. CPUs, the higher the number for the CPU, the better and faster it's going to be. And it's the same with this. So if we double what we have as our resolution, then that's going to be a better quality because it's converting that amplitude to a much better accuracy. So that's what they're getting at in this question. And that's what they do tend to ask about for sound. So what was the question again? Where's the question sheet gone? There it is, it's hiding. So explain why recording sound with a higher sampling resolution creates a more accurate recording. So basically you're using more bits to store the sound, and so it's going to be more precise. Now I think let me just have a quick look at the mark scheme, just to check I haven't forgotten anything. Oh yeah, so amplitude. So the more bits allocated to each amplitude, and the amplitudes can be more precise. There's a wider range of amplitudes can be recorded. Yeah, I preempted you there and you asked to see the mark scheme. So I think the key thing is try not to get mixed up with resolution for images. When we cover a paper that covers images, because they'll only do one or the other, they don't do both. It'll either be about images or it'll be about sound. They don't mix it. Image resolution is different. It's not the number of bits, that's the colour depth. So just kind of try not to get them mixed up. But resolution for sound is the number of bits for each sample. And then to speed it up, so it says give one other way that the way that the accuracy of a sound recording can be improved. Well, we've already talked about the bits, but it's the sample rate. And I did talk about that there. So basically the higher the sample rate, the better the quality, because you're doing it more often. So instead of like big gaps, you've got more gaps here, and therefore, you've got more samples, and therefore the gap between the samples is less. And so instead of like going from here to here, it's going from here to here to here, if that makes sense. Yeah, good. that's pretty much all you need to know for sound, actually. That these questions here are very typical, and there's nothing really else to know. For GCSE anyway. Let's move on then, and we've got some von Neumann. Love it. Okay, so a computer has a central processing unit, a CPU. The CPU includes the registers, the program counter, memory address register, memory data register, accumulator, and current instruction register. The table contains 5 statements about the role of registers in the fetch, decode, execute cycle. 2 of the statements are not correct. Identify the letter of each incorrect statement and suggest a corrected statement. So we're just going to put which one it is and then the corrected statement. I will quite happily go over the von Neumann architecture if you want me to. In fact, I probably will actually. I think I will go over it. Did I just see a whole load of people leave the live stream when the von Neumann came in? I think it's worth it. I think I'll go over it slowly. So there's a couple of answers there. I'll tell you which are the correct ones. So, the incorrect ones. The incorrect ones are B and C. Okay, so B and C are incorrect. The MAR, MDR are both the incorrect ones. So the PC, the program counter, stores the address of the next instruction to be accessed. The accumulator stores the result of each calculation. And the current instruction register stores the instruction currently being executed. Yeah, the PC is the to-do list, that's right. So the MAR doesn't store instructions from the program that is running. It's got an A, which is addresses, so it means it stores addresses, not instructions. And then the MDR stores data passed to it from the PC. Well, it does store data, but it's not from the PC. It's from just the input or output device, or the hard disk, or the RAM. So it's passed from, yeah, it stores the data of the address of what comes from the MAR. So if we have a look at the mark scheme for that, and I'll go through this anyway, I think it's worth, whenever von Neumann comes up, to talk about it. So statement B, the MAR stores addresses and not instructions. Statement C, data is from the bus, not the PC. So they put the bus, or is from address in the MAR, not the PC. So let's just go over von Neumann architecture. I think it's worth doing it. Because remember, like with the fetch, decode, execute cycle, it is one of these things that they do like to cover in the exams these days. I don't know why. I'm not particularly fond of it, but interestingly, some of the most kind of sneaky computer viruses, they kind of intercept the fetch execute cycle and sort of hide away and do bad things to your RAM during the fetch execute cycle without you knowing. So knowing about it is quite handy, especially if you want to go into cybersecurity or engineering chips and stuff like that as well. Okay, so let's just go over the fetch, decode, execute cycle. So remember that when we have the fetch, decode, execute cycle and everything in the von Neumann architecture, we have our CPU and we have our RAM, just like we always have, and they talk to each other with parallel wires. We also will have our hard disk or solid state disk or whatever it is. And in our solid state disk, we have all the software that we install. And then when we click on that icon to load it up, or we're opening up Word or opening up Excel or whatever it is, it will go from our hard disk and it will get loaded into the RAM. Okay. All the instructions for, let's take, for example, Microsoft Word. We've got Microsoft Word installed on our hard disk, and that gets loaded, all the instructions, into the RAM when we want to use it. Now, then what happens is the CPU, we need to fetch, in order to run Microsoft Word, the CPU needs to fetch all the code that's stored in the RAM. So it will get the first one, it will fetch the first line of code, or it'll fetch a list of instructions to get it, and then it will decode it, do some decoding, and then it will execute it. It will then send a message back and say, I need to get the next instruction, and it will fetch the next instruction, it will decode it, and then it will run it. Now, if there's any kind of like data to go back to the RAM, it will get sent back to the RAM as well by the CPU. But if there's anything that is kind of, it needs to keep, it will be kept in the accumulator. So that's kind of what we're looking at. The overview is we've got the fetch, decode, execute cycle, and we are fetching our instructions that are in the RAM, and it's sent back to the computer in order to be executed. So if we drill down a bit on that and we look at the von Neumann architecture a bit more detail, effectively we're kind of looking inside the CPU, and we've got our arithmetic logic unit with our accumulator in the middle, and the arithmetic logic unit is just full of logic gates, and it's the brain of the computer. We've also got our control unit, and our control unit controls everything, funnily enough. And we've got our current instruction register, and all that stores is what it said in that question. It just stores the instruction that the arithmetic logic unit is currently running. We've also got our program counter, and this is our to-do list of things to fetch. And we will have our, well, I'll put RAM here, but yeah, we've got our memory unit here, and the memory unit is usually on the CPU rather than external to it. So this is a little bit of memory inside the CPU that it needs to get the instruction. So we send it to our program counter sends the address of the next instruction to fetch from the RAM. And that goes to the memory address register. And then the memory address register says, go and give me, I don't know, whatever the address is. So the address could be 004. And that data inside 004, which obviously will be binary because that's what they store, it will then send it to the memory data register. Once that's arrived, the control unit will probably send a signal, or it might do some decoding. So all decoding is done in the control unit. Decoding is just fetching data that it might need to run that instruction that it's just got. So it could be that actually there's a little bit of data here further in the RAM that is needed for that instruction, and it will just go and get that. Otherwise, it will then say, okay, arithmetic logic unit, here's your instruction, run it, store a copy of it in the current instruction register, and then the arithmetic logic unit will run it. And then if there's any temporary data, it will store it in the accumulator. And it just does that over and over again. So this is kind of like the fetch bit. The fetch bit is the biggest bit, actually. Fetching, sending the address, go to the RAM, get the data, put it back in the memory unit. That's the fetch bit. The decoding bit, once everything's been fetched for that instruction, it will then do some decoding if it needs to. And then the execute is the middle bit here, just the CPU. I haven't talked about buses, so remember that we've got different buses. Buses are just wires between these. Obviously, they're usually microscopic, but we've got an address bus. So this here, I don't know why I've drawn it separately. This is the address bus here, where it's sending addresses. Funnily enough, this will be the data bus because it's sending data. And then all over the place, the control unit will have the control bus just sending instructions of what to do. Okay. So I'll go over von Neumann whenever it crops up, because I think it's better just to go over it and keep going over it, and it will get in your brain eventually. How long have we got left? About 5 minutes, so we can have a look at the next part of that question. So we've got those two corrected, and it says, oh yeah, they seem to like asking these questions as well. A computer has a single core 3.5 gigahertz processor and an 8 kilobyte cache. So the cache is what I was talking about here, not here, here. Effectively, it's the memory unit on the CPU is pretty much the cache. Anyway, we don't call it cache though if we're looking at it in this way. So state what is meant by a 3.5 gigahertz processor. And really they're kind of thinking about how many times it can process data per second, or yeah, how many fetch execute cycles it can do per second. That's what they're looking at. Anyone want to hazard a guess? I think this is the only time they've actually asked about it in this way. So basically all it means is it can run 3.5 billion fetch execute cycles per second. So it's just 3.5 billion gigahertz, or gigahertz is the equivalent of billion. So 3.5 billion fetch execute cycles or instructions per second. So it's quite a lot. I don't know why. I don't think they've asked a question like that since. Sometimes the papers for the March papers can be a bit weird. But yeah, 3.5 billion fetch execute cycles. Yeah, brilliant. Excellent. Yeah, good. Okay, next question then. I got a bit longer. So the CPU is changed to a dual core 3.5 gigahertz processor. Explain how the number of cores affect the performance of the CPU. Okay, so for this question, let's think about cores on a computer, on a CPU. So if we've got our CPU and it's got basically what is a core? So a core is basically an arithmetic logic unit. Okay. So normally chips would have one core. You also have the accumulator as well, but for all intents and purposes, it's the ALU. So if we've got more than one ALU, we've got dual core, for example. So we've got two. How many did it say added? Was it 2 or was it 4? Dual core. So dual is 2. So we've got 2 cores. We've got 2 arithmetic logic units. So effectively, well, we're not doubling. You can't double, and I'll tell you why in a minute. But some instances you can. It depends on what you're running. But the more cores, the faster it's going to be, because you can run more instructions and fetch execute cycle at any point. So the more cores equals faster computer, or faster performance. Now the only downside of that though is they do have to talk to each other. So you can't just have two cores that are completely unique. And if you're running some instructions on your CPU, they have to decide who's running what. And we get into problems where, for example, so say, for example, just a really simple calculation, like we have, I don't know, 3 plus 4 plus 9, okay? So we might allocate 3 plus 4 to this core, and then we might do the result of that, or whatever is left over, to the second core. So that one does that bit. But then if this core does the plus 9, it needs to know what the answer is to 3 plus 4 before it can do the plus 9, because it's got nothing to add it to. So although adding cores technically does give faster performance, not every instruction can be run in parallel like that, if you see what I mean. So it just depends on what is being processed by the computer. Most of the time, though, it does work and it is faster. But if you think about, if you've got a quad core, so you've got 4, I mean, my computer that I'm running this lesson on is a Apple Mac. They all have to talk to each other. I've got 8 cores on that one. So they all have to talk to each other. And they all have an arithmetic logic unit in them, but they need to coordinate and say who's doing what. And that can slow things down. So it's not a case of you can just have 8 million cores and that's going to be the best processor ever. It doesn't work that way. So yeah, so if we just have a look at the mark scheme, it says more cores increases or improves performance. More cores mean the fetch, decode, execute cycle instructions are more executed per second, because each core runs a fetch execute cycle simultaneously. Or not, if you look at that example. But you get the idea. It does improve it. Right, we've just got one more question in this section, well, kind of section. So we'll just do this next one, and it talks about increasing the cache. So we'll just do that one quickly, and then we'll go on to primary, secondary storage next week. So it says the amount of cache is increased to 64K, and it was how much before? It was 8K before. So from 8 to 64, explain how the amount of cache affects the performance of a computer. So this basically just goes back to what I was saying earlier about the von Neumann architecture. It's going to, if you increase it, we've gone from 8 to 64, anything on a computer that goes from a small number to a large number is always going to be better, without exception. But if we think about our von Neumann architecture here, effectively the cache is in the memory unit. And this is what we call static RAM. And the more you have, the more sort of space you have in the memory unit or the cache, the less you have to go to the RAM. And although the RAM and the CPU are physically close together inside a computer, it still does take time or longer to go to the RAM to get something. Whereas if it's on the CPU and it's your memory unit here, your cache, then it's going to be quicker. So the more space you can have for that on the CPU, the faster it's going to be. So that's what they're getting at with this one. So effectively, if we look at the mark scheme, it says the more cache improves performance, always the way, because more cache means the processor can access more frequently used data or instructions faster instead of having to access them from the RAM or slower RAM. And this is true. I mean, this is one of the, I say it's in my live lessons and everything. My computer is an Apple Mac with an M chip. It's got an M as in M for Maestro or whatever. And they were a big improvement. I think it was about 2018, 2019, something like that, when they brought the first M chip out. And it was absolutely astounding. I mean, they massively improved CPUs when they brought them out. Intel and AMD, who are the main other chip manufacturers for PCs anyway, it's taken them years to catch up. They have caught up, but one of the big improvements that Apple made to their M chips was they massively increased the amount of cache that their CPUs had, and that was one of the things that has made them super fast. There are other things as well, but that is one of the big things. And the only problem with it is static RAM that's used for cache is more expensive, so it does cost more money, but it is faster. So yeah. Okay, so we'll finish there, and next Wednesday, we'll carry on. So if you did want to try some of the questions, it's the March 2024 paper. There's only 2 papers that, the theory and the programming for the March papers, if you want to give it a go. And I'll see you next week. Take care, everybody.